In this next part, we will be building our program counter. The CPU needs a program counter so it can keep track of which instructions it is currently executing and also to be able to execute the next instruction, how it will know which instruction to fetch from memory or to read from memory. And for that, we will build a counter, a binary counter, and we will base it on the 74HCT161, which is a synchronous 4-bit counter. So we'll use two of them, and they will be connected in a way that they will become an 8-bit synchronous counter. With each clock cycle, the counter increments 1 bit, so it will count from 0 to 255 in binary. And also a good feature of these chips, the 74HCT161, is that they have the ability to load data into them. So not only can they count synchronously, and we also can use them to as a register. So we can implement our jump instructions, which we will get to later on, by means of these load data on the counters. So it can count not starting from 0, but from any number we happen to load into the memory of these counters, into the registers that they have. And in order to interface the counter to the bus, we will be using the 74HCT245, which is an octal bus transceiver, which is a tri-state device. They have 8 tri-state buffers inside, so they can interface whatever we want, in this case the counter register, to the bus, and in which we can say connect or not to the bus, open circuit or connected to the bus. So we can input the data from the counter to the bus. We will place the program counter beside our clock because it fits there. That's the only particular reason. We have enough room to fit the chips we need for the counter and the LEDs, and also leave the space that I'm saving here on the side for half of the bus, which are 4 bits of these rows, and the other 4 bits of the bus will be built on another board that will connect to this one later on. So we'll just go quickly through the program counter schematic. And as I said, it's based on the 74HCT161, in this case the LS161, which are compatible, and the 74HCT245, which is the bus transceiver. And we'll connect them in such a way that the bus will be directly connected to the input of the counter, of the register of the counter. So if we want to get the data from the bus to set our counters, we will just need to use this control signal here, which is the program counter in, and then it will accept the data from the bus. If we want the counter to count, we'll just set the program counter enable high, and it will count. The clock pin will be connected to the clock because this is a synchronous program counter, and the clear that we can use to reset the counter, which will also be connected to the control logic. And on the buffer side, on On the transceiver side, we have the program counter out, which is the enable from the buffer, which will take the output from the counter and connect to the bus. And of course, the output from the counter will also be displayed in 8 LEDs, which will directly connect to the counter by means of current limiting resistors. And not to forget the 3 smoothing capacitors on the input of each of the integrated circuits. So after another few hours of soldering, that's what they got. The program counter is built, and all these blue wires here, there's a mess. They are the control lines. That's why they are so long, because they must reach down to the control logic when we build that. But for now we could test it. I've just jammed all the control wires here under this resistor, which is connected to VCC, and so we should see the counter works, because as mentioned before, the halt clock is a negative high. So if we connect it to VCC, it won't halt the clock, so it will count. And we have the count reset, which is also negative logic, so we connect to VCC, it won't reset. And we have the counter enable, which is positive logic, so to VCC it will count. And here we have the load, so we can load a value into the counter. It's negative logic, so we connect to VCC, we won't load anything. And at last the counter out, so we output the contents of the counter to the bus, is also negative logic, so we don't want to output it now, although it makes no difference. But if we just jam all the control wires now to VCC or under this resistor here, we should see the counter count. So let's see. Great. Exactly, it's counting, and we can accelerate a bit the speed. And it's counting from 0 to 255. We can test it if we can stop the clock and manually advance it. Yeah, it's working fine. Great. Also, I will note that I have decided to change the resistor that is powering the clock LED, because this blue LED is very bright. So I've substituted it for a 4.7 kilo ohms resistor instead of a 420 and 470 ohms. So a 10 times larger resistor than before, and it's still very bright to me.